This video is an introduction to parametric equations. Parametric equations are a method for describing curves using two independent equations for x and y rather than describing y as a function of x. We do this by introducing a third variable, t, which we call the parameter. Let's take a look at an example of this. Here we have an equation for x and an equation for y, both described as functions of t. We can also write this as x of t to highlight the fact that x is a function of t and y of t. Notice that x and y are independent. X and y only depend on values for the parameter t. The values of the parameter could be from negative infinity to positive infinity, or we could choose to restrict the values of the parameter. When we restrict the values of the parameter, we'll see only a portion of a two-dimensional curve. Let's talk about how to sketch this curve. Remember when you first learned how to sketch two-dimensional curves? You probably made a table of values. Usually x is the independent variable, so we chose possible values for x and then wrote out what the outputs from y would be. We'll do a similar sort of an idea with parametric equations. Here, the parameter t is the independent variable, and x and y are both functions of t. Let's fill out this table. If t equals negative 2, x is t plus 1, so x would be negative 2 plus 1, negative 1. If t is negative 1, x is negative 1 plus 1, 0, and we can see how to fill out the rest of this column. Let's do the same for the y values. If t is negative 2, y is equal to 2 times t squared. Negative 2 squared is 4. 2 times 4 is 8. When t equals negative 1, y is 2 times negative 1 squared. Negative 1 squared is positive 1 times 2 is 2. If t equals 0, y also equals 0. If t equals positive 1, y equals 2. When t equals 2, y is equal to 8. And when t equals 3, plug 3 in for t, we get 9 times 2, y is 18. Now we'll treat these as points, negative 1, 8, 0, 2, etc. And let's plot those in the two-dimensional plane. Negative 1, 8 is here. 0, 2 is somewhere around here. 1, 0, something like that. 2, 2, 3, 8, and finally 4, 18, somewhere up here. If we connect these points with a smooth curve, we'll get something that looks like a parabola. Notice that we only have a finite portion of a parabola. When we limit the value of the parameter, we only get a finite portion of curve. If we allowed the parameter to vary from negative infinity to positive infinity, we would get the entire parabola. Notice also that this curve has a direction. As t increases, the curve is sketched from left to right. We can add an arrow to represent the direction in which this curve is sketched. Let's look at how to sketch parametric equations in Desmos. Here, we can create an ordered pair where the first coordinate is the x function, the second coordinate is the y function, and we can add where we would like the parameter to vary, in this case from negative 2 to positive 3. I've added in this point here where we can see the points of the curve as they're sketched out when the parameter varies. We can describe many interesting graphs using parametric equations. Here's one example. If we take x equals 4 times sine of t, and y equals 2 times cosine of 3t, and if we let the parameter range from negative pi to positive pi, we get this graph. Notice here that x is not a function of y. This does not pass the vertical line test, but it's a perfectly good curve that we can describe using parametric equations. Here's another interesting curve. If we think of the parameter starting at negative 2 and then increase the upper bound for the parameter, we can watch this curve being sketched out. It almost looks like the path of a comet circling around the sun. One final example, just to illustrate how interesting parametric equations are. Let's not worry at all about this expression here. It's some complicated expression with sines and cosines, but take a look at the cool graph that we get here. We can sketch many interesting graphs using parametric equations. Let's do one more example using parametric equations. We would like to eliminate the parameter in the previous example to obtain a Cartesian equation of the curve. Let's write down the parametric equations that we were dealing with. We had x equals t plus 1 and y equals 2t squared. To eliminate the parameter, we want to solve one of these two equations for the parameter t. In this case, it looks like the x equation will be the easiest. If we solve for t, we will obtain t equals x minus 1. Now, we can plug that expression for t into the y equation. If we do that, we have 2 times x minus 1 quantity squared. This gives us the Cartesian equation, y equals 2 times x minus 1 squared. If we graph that equation and compare that to the parametric equation, notice that this Cartesian equation is the same parabola. However, when we eliminate the parabola, we lose the directionality of the curve, and we also lose the fact that we had just a finite portion of the curve.